Hi. So after Igor's superb exposition of the state-of-the-art construction of relaxed locally decodable codes, I'm here to be telling you about the bad news and about the limitations of relaxed LDC. And we'll explore a new paradigm for proving lower bounds for these objects, which goes to a very nice notion of relaxed sunflowers, to which we refer as daisies. And so without further ado, let's get started. So recall the story so far. We have we know that the best OAuth1 queries relaxed LDCs, the best OAuth1 queries LDCs that we have this sub-exponential length, which is not ideal. It's very redundant. And we have this theorem, which Igor just showed, that there exist constant query relaxed LDCs with nearly linear block length. And by that I mean we're mapping k bits message into n bit message, such that n is equal to k to the power of 1 plus small epsilon, as you can see here. Okay, and this is for an arbitrarily small factor, epsilon. And again, if you didn't see the first introductory lecture, if you're not sure what relaxed LDCs are, I strongly suggest to check the first introductory lecture where we capture exactly all of the definitions and establish. So this is just a quick recap. Okay, so now back to an open problem that Goldreich raised in 2004. So after constructing this nearly linear relaxed LDCs, there is the question of whether can we do better. So what does it mean better? Maybe we can go, so we have this like one notion of being nearly linear, which is, k to the power of 1 plus a small constant. Better than that would be k to the power of 1 plus little o of 1, something which tends to 0. And even better thing to wish for would be to look at quasi-linear lengths. So n being k polylog n, and perhaps even constant rate. That would be the most amazing. In some sense, this is also interesting because remember that the upper bound that we have sort of matches the lower bound that we have for non-relaxed LDCs. So if one wants to separate between these two notions, then either one has to strengthen the lower bound for non-relaxed LDCs or improve the upper bounds for LDCs, which we still don't know which one of them is possible. And notice that obtaining a lower bound for relaxed LDCs is not trivial at all. And the reason being, so there are quite a few reasons, but the main reason is that the main argument that appears in pretty much all of locally decodable codes lower bound techniques is that we are using the equivalence of LDCs and smooth codes. Well, smooth codes are codes in which we query each location with roughly the same probability. And now, so we don't have any locations which are extremely concentrated. Now, even if we go back for a second to the first construction of PCPs by BGHSV, where we had the message, the code, and the PCPs, then notice that if we want to query coordinate x1, then with probability 1, we will query x1, and we will strongly query the PCP1. So this is highly non-smooth. And in fact, this is in some sense where relaxed LDCs get their additional power over LDCs by not being smooth. And since the argument for lower bounds relies so strongly on smoothness, This creates a big challenge. Recently, in joint work with Oded Lachish, we essentially answered this question with a strong no. And what do I mean by that? So what we will see in this lecture is a proof for the following theorem. So the theorem will tell us that every O of 1 query, relaxed LDC, with constant decoding radius, which is essentially the regime of distance that we care about, satisfies that n has to be omega of k 1 to the epsilon for some constant epsilon. So this means that what Ego, the construction that Ego just showed, is more or less optimal. And in fact, the bound is nearly tight in that respect. Though there will be a caveat that Ego will discuss in the last open problems question. So let's see how we go about proving this thing and how do we avoid this limitation, this barrier of not going through the equivalent to smooth codes, because our relaxed LDC will be highly non-smooth and we need to deal with them. Okay, so the high-level approach is as follows. We start with some code. This C, from 0, 1, K to 0, 1 to the N. And that's our relaxed LDC. We assume that it has a certain decoding radius and queries and so forth. And the strategy would be to start with the decoder that is implied by such a code, which is L local for some L, which is O of 1. And from this, we want to derive a global decoder. And the global decoder is the following algorithm. It's an algorithm that is given a valid code word. And so we have a guarantee that we have C of X, no corruptions whatsoever. So no error correction, just global decoding in the sense that it gets C of X, it makes some queries of it, and it restores and it outputs the message X. And now the point here is that since it is informationally, theoretically impossible to recover k bits of information, to recover it without making O of k queries, then this would actually imply a lower bound. So what we do, we say that, yes, we have this locality L prime, but we know that this L prime, the locality of the global decoder, must be at least as large as K, like that. And so we will get the following lower bound, if we can construct such a global decoder. And so in some sense, what I will show you, this is a nice paradigm, because it takes the hard problem of proving lower bounds into an easier problem of constructing a decoder algorithm using something. So it's a nice lower bound via algorithm approach. Now, for the sake of good order, there are some assumptions that we need to make, and I'll quickly tell you what they are and why we can make them. So the first assumption is that we'll make that the decoder, that the local decoder that we get from C, makes non-adaptive queries. This means that the query sets are predetermined. We cannot probe a coordinate and based on what we see, probe the next one and so forth. Now, in general, we can't just assume it without loss of generality. But what we can do is we can start by saying, fine, let's do some transformation which we will lose a little bit we will lose somewhat significantly, but not to the point which is degenerate. So we will lose in the locality in the parameters that we get, and this will allow us to get non-adaptive queries. So for those of you who are more familiar with this transformation, it simply means replacing a decision tree by all of the points that, that can be queried. And I will later tell you about how one can do it in a more clever way and essentially lose nothing. So that's the first point. The second point is we'll assume that the relaxed LDC, if it is given a perfectly valid code word, not only it will not output a BORT, but it will always manage to decode a valid code word with probability 1. Again, this is not something which is necessary, but it requires quite a bit of work to overcome it. And for the sake of simplicity, I will avoid both of these issues, though I will discuss them in my last slide or so. And then two other properties are quite simple, quite straightforward. We'll assume that the error, so like the probability that we will succeed would be 1 minus this O of 1 over L squared. So this we can always do by just like doing simple error reduction. And the last one, we need to bound the randomness complexity. And there are known transformation based on the Goldreich-Sheffitt theorem, which allow us to do this without loss of generality. Okay, so tedious comments aside, we can get started with the interesting part. Okay, so how can we get such a global decoder? It's a tricky question. So the first thing that we have to do is to adopt a new way of looking at it. And this is where we strongly use the non-adaptive perspective. So what we can say is we can take the relaxed local decoder D and view it as a collection of distribution and predicates. So this is a bit of a tedious description for something which is quite intuitive and simple. So the point is, we have this decoder and it queries certain points. So it has a local view of its objects. So think about each one of these yellow circles here as representing some L coordinates, which the decoder might do. And so what do? We pick, according to some distribution mu I, we pick one of these sets, one of these yellow ovals here, and then we query it entirely. This is our local view. And then we have these predicate functions, which correspond to each one of these sets, and based on which we can rule. And by our assumption over the randomness complexity of the having like small randomness complexity, then it means that we only have O of n of these sets which are supported. Okay, so this is a fairly simple way of viewing any query algorithm, non-adaptive query algorithm, just a distribution over the set that it queries. And we also have some functions which allow us to rule for with respect to what we have. And I notice here that I forgot to mention, this is not just a function of I, the coordinate that we wish to decode, but also of the specific subset that we want to do. Okay, so now having this perspective, which is completely combinatorial, or not completely combinatorial because we still have probability, but it allows us to think about it in more combinatorial terms, we can ask, can we emulate this local decoder by looking at this algorithm which goes coordinate by coordinate and queries it with a certain small probability? Okay, so let's see what does it mean. So what we want to do is to do some random sampling and somehow emulate D. So let's see if this makes sense at all. So let me start with the easiest of all cases, because we want some, reason for optimism, especially now in COVID days and all of these things. So suppose that we have mu I, which is the distribution over queries that the decoder is making, and suppose it is well spread. Well spread in the sense that maybe let's take it to the extreme and say that the query sets are completely disjoint, or they might have a few intersections. You'll see this in a second, it doesn't matter, but suppose that they are completely disjoint. Then what is the probability that we will get a full set of L coordinates, like a full set, one of these S1, S2, S3s, by random sampling? So the point is, for any particular Sj that we want to look at, we have L coordinates, and each coordinates will be sampled with probability P. So we're getting P to the L, which in this case is 1 over n to the 1 over 2L, fine. And the point is, because we have linearly many sets, then not only we will get a set, a local V of D, but rather we will get n to the 1 minus 1 over 2 to the L set. So we actually expect to get a lot of sets, and then we can easily emulate the invocation of the local decoder. Okay, so this is all well, but of course, there is no reason whatsoever for us to think about that the decoder would be spread. And in fact, it's not easy, it's not hard to show that such an algorithm would be extremely limited. And indeed, all of the constructions of relaxed lists that we have are extremely dense, and they are complicated, and there are lots of intersections. And so one can ask, what happens if the coordinates are concentrated? And to take this to the extreme, just to illustrate the problem, let's look at the following scenario. So suppose that we have a decoder which is extremely biased towards one coordinate. So for example, there exists this one coordinate J, and this coordinate J is being queried with probability 1. Notice that this is not a completely hypothetical example, but the same BGHSV decoder that I mentioned, the one with X, C of X, and the PCPPs, we explicitly read the coordinate X1 with probability 1, or to decode, like if we want to decode Xi, we will read the ith bit with probability 1. So this is not a ridiculous example. And in fact, all constructions of relaxed LDCs, part of the power is because they can concentrate the queries and not be smooth, otherwise they would coincide with standard LDCs. Okay, so suppose that this is the case. Then what is the probability that we will query any set? So the point is that, and I see here that I'm, being inaccurate. So this is less than, but it doesn't really matter. So the probability that we will query any one particular set is depending on our ability to query this coordinate J, because all sets contain this J. And so we know that querying J we do is probability P, which is 1 over n to the 1 over 2L squared. And that is very, very bad. So it means that like, there is a negligible probability in which we will recover any of these sets. Now, to make this approach even worse, then for each one of the queries that so recall that the decoder, it gets an index for decoding, this index I, like which index of the message you want to decode, and for each one of them, there is a completely different distribution, mu I. And so each one of these mu I may concentrate the queries on a different J, as happens in the BGHSV code. And so it means that we can have linearly many heavy coordinates. So this seems very, very problematic. And I remember the time talking to Oded Lachish, my co-author in this work, and I was extremely skeptical that this could work. But it turns out that this is not so hopeless as one might think. And let me show you. Let's start with this simplest case and see how we can deal with things. Okay, fine. So we have here the following thing. So suppose that we're focusing on this particular coordinate j that is being queried with probability 1. So we know that if we're just randomly sampling each coordinate with a tiny probability, it's highly unlikely that we will hit this j that we care about. But we are talking here about locally decodable codes, relaxed locally decodable codes, and they are robust to errors. In particular, if there is a coordinate that is being asked with probability 1, and this coordinate is corrupted, then the local decoder knows how to deal with that, right? And in some sense, we can observe that the following phenomenon happens. So if we are just guessing the value of w at point j, the value that we don't know, and if we got the correct guess, then we know that all of the local views, all of these sets sk, will decode correctly. This is because we are assuming that given a perfectly valid code word, we are happy. And if we are making, and by happy I mean we decode correctly. And if we made a wrong guess, so we have a point which is corrupted, and this point which is corrupted, if we were to invoke the relaxed local decoder, then it means that the majority of the sets would not lead to a mistake, which in turn means that either we'll get the correct value or we'll abort. And it's important to stress at this point that this all holds because we are looking at a global decoder, which is promised to get a completely valid code word. So all corruptions that we might see are things which happens if we guess, because everything that we query will have to be correct by our assumption that the global decoder gets valid code. Okay, and I want to just quickly make a quick remark about non-relaxed LDCs. Well, in that situation, things are even much easier. So if the LDC is not relaxed, it means that not only we'll have this like on correct, we will decode correctly and otherwise to be correct or abort, but rather we know that with high probability, we will always output the correct value. And so we can do something, as you'll see later, which is much more naive. We can like literally just guess and not do something more. We just assume maybe like that there is 0 all around the place and invoke the local decoder in this case. Like for example, we can just like always assume that j is 0. So we don't have to analyze what happens if you made the correct guess or wrong guess. And you will see that because in the setting of relaxed decoders, we might abort, then it's very important to keep track and of the behavior on correct guesses and wrong guesses, and we can't just use robustness. But this will become much clearer soon. Okay. So let's continue. So the first observation to make is that what we just discussed doesn't apply just to the case where there exists a single coordinate that we query with probability 1, but it rather generalizes to combinatorial sunflowers. And what we mean by that, recall that a sunflower is a collection of sets which, well, looks like a sunflower. Or more accurately, it's a collection of different subsets of n, let's say in this case, such that the pairwise intersection of each one of them is the same. So for example here, if you look at this sunflower here, the thing to imagine is that each one of the petals is part of a set which also contains this kernel K. And together, so this would be one set, and that would be another set, and they all intersect exactly on K. Now, so whereas before we had a sunflower with kernel of size 1, now let's suppose that it just happened to be the case that our local decoder has a larger domain K. So the observation to make here is that as long as this kernel is of size which is less than the decoding value, this delta 0 that we have for the relaxed decoder, how many errors we can tolerate, then we can just do the previous argument and be done with it. And so this gives a very naive idea, which fails miserably, which is, we have this tool back to the days of Erdos and Rado, where we can take any arbitrary collection of subsets, like, for example, these subsets here. We can take each one of them and extract a sunflower out of it. So here in this example, we'll see this red, I highlighted by red. You see in this collection, it actually contains a sunflower. And in fact, we can show that the sunflower lemma shows that for every such collection of sets, there exists a sunflower. However, if you look at the state of the art, and also there are lower bounds that match it, that this sunflower would not be big enough. And notice that for us, for this to make sense for this argument, we want to have a sunflower which essentially approximate all of the local views, because we want to zoom in and only rule according to this sunflower. And now, if the sunflower takes a very small fraction of the sets, then it might be the case that all of the errors that we can tolerate fall in this particular case, and then we'll have a much larger fraction of error than we can tolerate. So the problem is that because the sunflowers are not of size linear, it's not just some constant fraction of all sets, but rather something which is sublinear in that, then it is not a good approximation of the behavior of the original algorithm. And so this idea fails miserably. But we still have an important small victory here, that in some sense, the biggest fear, we had this one extreme case of all the sets being well spread, and then we're happy. And then if they're all extremely concentrated on a single point, then we're happy too. But the question is, what happens when we have, this ugly mess here where intersections are numerous and hard to, how do we even deal with that? And this is where the notion of daisies comes into play. So the point is, yeah, we might not be able to find a sunflower which is large enough, but maybe we can use something which is less than a sunflower, something more relaxed. And indeed, we'll consider the following relaxation of sunflowers, which we fondly refer to as daisies. And let me start by giving the following definition. So we say that a sunflower is a tea daisy if it's a sunflower, but it also allows this looseness and slackness that sunflowers do not have. So it relaxes it in two ways. The first thing is that the kernel need not be the intersection. So what do I mean by that? Rather than saying that there exists a single point, a single kernel, where each two sets intersect exactly on that, here we say, well, maybe we have this set here, and it just touches this kernel, and then maybe we have another set here, and we don't know how it behaves. So all we care about is that we can draw a certain circle such that outside of the circle, we'll have a nice sunflower structure. Now, just to mention a point of triviality, one can always choose a very, very, very large kernel. For example, the kernel could be everything. So we want to control the size of the kernel. And notice that in our setting, we want to control the size of the kernel such that it would be at least sublinear. So we'll see that in a second. So the first relaxation, it tells us, well, take a sunflower, but instead of having perfect intersections, you can have a mess within the kernel. The kernel need not be nice. And the second intersection and the second relaxation tells that outside of the kernel, there will be a limited amount of intersections. So what do I mean by that? So for any point which lies outside of the kernel, like for example, let's say this point here, we want this point to be covered by at most T petals, right? So recall these are the petals and the kernel is inside. So inside the kernel, we have no guarantee whatsoever. It could potentially all sets touch these points in the kernel. So the degree of point in the kernel might be unbounded. But outside of the kernel, each point is covered by at most T's of the sets. So this is the relaxation. And the beautiful thing about this relaxation is that one can get worse. We can only get sublinear and small sunflowers out of an arbitrary collection. With daisies, we can get huge daisy out of any collection that we'd like. And this is being shown by what we call a daisy lemma. So what does the daisy lemma say? So it's like, it looks a bit messy, but let me break it down slowly, and I think it will be very clear. So first of all, one thing that I kind of did not refer to explicitly at this point is that recall that we want to emulate some algorithm, and the algorithm does not necessarily choose each one of the local views uniformly at random. Maybe this particular local view is being asked with very high probability, and this, oops, wait, okay, I'm doing this, okay. And maybe this one here is being asked very rarely. So instead of having just a collection of subsets, we want to have a distribution of linearly many sets, each one of them of size L, right? And each one of them, this exactly tells us, like, we have this distribution ui, which tells us that the algorithm, if I want to decode the bit number I have a distribution over these sets, and I fit all according to that. So the daisy lemma, rather than talking about a large collection of subsets, it talks about subsets with heavy weight. So, so it takes into account that as well, and strictly generalizes the notion of a purely combinatorial daisy. And we extract a T-daisy with the following properties or parameters, and I will try to say why we need each one of these things. So first of all, there is the density, like the weight of the daisy. And this is like having a large daisy. So in this case, it means having a heavy daisy. And the importance here is that we want this daisy to be a good approximation of the behavior of the algorithm. So in particular, recall that after the error reductions, we know that the algorithm succeed, like there is only probability of 1 over L squared that if we pick one of these subsets, we will get the wrong answer. So because the density is so large, it is 1 over L, so the total, so out of that, the amount of errors is just like the probability of choosing something well is 1 over L minus 1 over L squared. So we have a very good approximation of the set. This means that if we are choosing if we're choosing conditioned, if we're choosing a local view conditioned on being in this daisy, then we still get with high probability a correct answer. Now, the second condition tells us that the kernel should be of size n to the 1 minus s over L, where s is some bound on the petal size. So this is a bit technical, but the main point to take it from here is that we want the kernel to be smaller than the decoding radius. Okay, now the last point, and the reason why we want it to be smaller than the kernel is because the decoding radius is because we want to be able to guess or enumerate or not sample these values of the kernel, but only sample things which lay outside, and we want to have the robustness to error to support us in that. Okay, and the last point is the t-daisy here. And so the number of intersections that we have which are outside of the kernel is bounded by this sublinear number again. And here the point is, remember that we said that if the outside of the kernel, everything is disjoint, then we had this easy argument of saying we have linearly many petals. And so the probability of querying each one of them, of querying at least one of them is pretty high. So the point is, here, if you take some sort of a Janssen type of lemma or Heinel-Samredi type of lemma, then one can show that with high probability, despite this intersection, we'll still sample a whole lot of petals outside of the kernel. And so, whereas before, we only had this like tiny sunflower, now we are guaranteed that we'll have a very large daisy. And notice here that you can exactly see that we have the core itself, the kernel, contains quite messy intersection. It's not exactly the intersection. And there are some, this is like t equal 2 in this drawing because we have points which are covered by 2 sets. Maybe, yeah, I think 2. Okay, so that's the notion of a t-daisy. And the point to take is that we have a minor relaxation of the notion of a sunflower that allows us to get a very, very large, relaxed sunflower or a daisy. Okay, and now, without further ado, we can show the algorithm itself. So it might seem a bit complicated, but it's actually quite simple. So let me do it step by step. So how do we use these daisies to get a global decoder? Well, here is what we do. We start by having this algorithm, which has query access to a perfectly valid code word C. And we sample each coordinate, just flip a coin, and with probability P, which is set to this number, we query each of the coordinates. At this point, we are done sampling, and we have one set of queried coordinates. We can call it Q, or it doesn't really matter. We will not longer sample anything. And then we have this loop where we'll go coordinate by coordinate, where the crucial point is that we will be reusing the same queries that we've used to decode all of the different elements. So what we will do for each one of them message bits that we want to recover. So we'll start by taking μi, which is distributions over local views that the local decoder would use. And from that, we'll apply to it the daisy lemma. And we'll get a collection of daisies with kernels. Now, I recall that we do it k different times, and it's important to note that for each one of them, we'll get a completely different daisy with potentially completely different kernel. We have no way of controlling that. But just for sake of convenience, I will omit the notation of the dependency on I and just call the daisy a collection of sets, SM, and the kernel K. So now we're zooming on one coordinate. Okay, and now we do the following thing. The point is that if we were just to guess some arbitrary value assignment to the kernel, then, well, we do have the robustness of the code, and we do have guarantee that we will not err with high probability, but it might very well be the case that we will just output bot. And we want to recover the entire code word and not just output potentially all the time bot. And so we have to do something more sophisticated. Though, by the way, that if we had just a standard LDC, not something which is relaxed, we can just indeed make a random guess. But the point here, because then we won't have to deal with the I don't know with the bot sign. But with relaxed LDCs, things are a bit more complicated. So what do we do? Instead of guessing an assignment, we will enumerate over all possible assignments to the kernel. Now, recall that the kernel is smaller than the decoding radius, and this means that like we'll have for each guess we would still be within the decoding radius. Okay, so we do this, and then we need for each one of these assignment to the kernel, we look at the collection of petals that we sample, that we actually sample, and we fill these petals into full local views by filling out the values that we get, that we enumerate over the kernel. So for example, let's say we've ended up here sampling all of these coordinates S1, and we made some guess to the kernel. So we actually have an entire local view, which is partially real and partially a guess. Now, recall that because we have linearly many sets on the one hand, and very few intersection outside of the kernel, then we actually expect to get a large number, to sample a large number of petals, which means that after we fix an assignment to the kernel, we can actually see how would the local decoder D would have outputted with respect to that. Okay, and now the following thing happens. Note that suppose that we just happen to be tremendously lucky and we have the correct assignment. In this case, by the guarantee of the relaxed local decoder, we know that with probability 1, we will decode the right value. This means that all local views, and in particular, all of the local views within the daisy that we're looking at, if we'll feed these values to the local decoder, then we know that with probability 1, it would always give us the right answers. So we expect to have a full consensus that all petals completed into full local views by our guess to the kernel, all of these would always lead to the right value. So these are represented here by the green petals, where green petals are good. But now, what happens if we are going over the wrong assignment to the kernel, which is what will happen most of the time. So then we'll have one of 3 options. Either we'll have petals that would give us the right answer, xi, or we might see some petals that give us the wrong value, like the opposite of that. Or finally, we might get to see bot. But the point is, because the relaxed LDC is promised not to err with high probability, so we know that with that most of the sets that we will see will actually either be bot or the right value. So it could be the case that there is a whole minority of the right value, like that we'll sample a bunch of petals. One of them would tell us that this is 0, 20 would tell us that this is 1, but we'll always have, in this case, say 50 that would tell us bot, because we know that the total of the right answer plus bot must be larger, significantly larger than the number of wrong answers. And so what we can do is we can consider assignment by assignment, look at all of the local views that we get by combining the guess of assignment to the kernel and the petals that we actually sampled. And if we see a consensus, we output that, because then we identify that we are here. And if we see any 2 petals that disagree, then immediately we know that we are here. And in this case, we can just output bot. And that's the main idea that underlies this lower bound technique. This is how one can build the global decoder. And I'll conclude by quickly mentioning the parts that I omitted and hopefully encourage you to look at the paper. So for my last slide, I want to mention some of the extensions and generalizations that we have. And some of them were done together with Oded Lachish and my student Marcel Dalignol. And in particular, what we've done is one can ask how to handle adaptivity. So before we said the following thing, we know that what does it mean to be an adaptive algorithm? So we can think about an adaptive algorithm as a decision tree. We first query the first coordinate we want to see. And if it's 0, we go here. And if it's 1, we go here. And then we proceed to the next coordinate. Let's say it was 0 and we're here. And then we look at the offsprings and we look at the second coordinate we query. And if it's 0, we go here. And if it's 1, we go to the other node. So each path along the tree leads us to a local view, to some tuple of coordinates we will read. Now, the point that how this is dealt with in a naive way is just by saying, well, let's say that we take this tree, and instead of having, let's say, queries of size q, we'll have queries of size, which is all the path that we have. So for example, here, if this is a tree of depth d, so we'll have 2 to the d different path. And for each one of them, we have a subset q, and then we can take the union over everything, and we increased exponentially the number of queries. But this is a way of making an adaptive algorithm non-adaptive. Now, if you want to do it in a smarter way and get tight results, then this creates a lot of difficulties. In particular, if you think about it, then we will have different sets that will be queried per input, and some of them would lead to completely different daisies, and we'll have different coordinates that will be queried by the algorithm with respect to any particular corrupted code that we'll get, and this makes a whole lot of difficulty. And part of the way to do it is we can't really just use a daisy lemma to extract one big daisy, but rather we'll have to partition all of the sets into several different daisies and aggregate results from all of them together. Another point that we didn't really discuss is the notion of two-sided error. So in the definition of relaxed LDCs, it's not necessarily the case that if you're getting a valid code word that you will always with probability 1 answer correctly. The only requirement is that we will not abort. And in order to deal with that, while it seemed like, what is the problem? So in this case, we don't have any consensus. And so it might seem simple because all we have to do, if you go back here, so suppose we don't have consensus. So this means that instead of having either all green petals or most petals would be green and blue, like correct or bot, we will just have in this case, a majority of green petals. And then it seems as if it's just like comparing two thresholds and doing a simple churn of concentration of measure argument. But the problem is much more subtle because we will use this daisy partition lemma, and we have different petals of different size. And if you have a petal of small size, which only contain maybe one coordinate, then it is far more likely that one will get it than a petal with size L/2, which is much harder to get. And so one has to do a much more refined analysis in order to get that done. And in particular, as part of the partition lemma that we use, we break down the the arbitrary collection of sets into a complete partition into daisies, and they'll have the following structure, that each one of them would have increasingly larger and larger kernels, which contain one another, and the petal size will decrease. So the first one would be petals of size L-1, which means that only one point is contained within the kernel and the rest are outside. And then the petal size will decrease and decrease and decrease until you'll have all that all of the petals are inside the kernel, except for one point which is outside, as you see in the right hand side. Okay, so, and the last point I want to mention that one can further generalize it and capture not only relaxed local decoders and LDCs, but actually capture a lot of other type of local algorithms, such as property testers, PCPs, and learning algorithms. And there's quite a vast potential for this type of combinatorial daisies and combinatorial relaxed sunflowers approach to analyzing this type of algorithms. So thank you for listening. And next, you'll have Igor mentioning several interesting open problems and directions. Thank you.